Hello. In this problem, two equal and opposite point charges are placed on the axis of a circular region of radius capital R, and we're asked to find the flux of electric field through this circular region. Okay. I think there are a couple of ways in which you can solve this problem. Okay, so let's wait for the noise to die down. Okay, so here I have taken a ring. We can call it a sample ring of radius r and thickness dr. Radius r and then thickness dr. So here I'm going to assume that you know the electric field due to a dipole. So we have equal and opposite charges separated by distance 2l. So that's a dipole for us. And any point on this circle, okay, so the circle becomes the equatorial plane. At any point the electric field would point in a direction opposite to the dipole. Okay, so the dipole points from negative charge to the positive charge, so that's the dipole, and the electric field would point to the right. Okay, so what is the electric field because of a dipole? This is 1 by 4 pi epsilon naught, the magnitude of dipole moment, which is q into 2l divided by l square plus r square raised to 3 by 2. Okay, so if I take that sample ring, the flux through the sample ring let's say d phi can be written as E into dA. Okay, so if I want the entire flux, I'll just have to integrate this. So let's carry out this integral. So what is E? So 1 by 4 pi epsilon naught q multiplied by length of the dipole by L square plus R square raised to 3 by 2 multiplied by area. So we know how to get the area of such a circular ring. It's like a circular belt. So if you cut it open, it will be a rectangle of length 2 pi r and then width dr. We're going to integrate from 0 to r. So here, to ease out the integral, I'm going to leave 2r dr in the numerator. The rest of the constant values I'll pull out of the integral. So I will get ql by 2 epsilon naught integral 0 to r 2r dr by L square plus r square raised to 3 by 2. Okay, so here I think I'll make an assumption that you know how to complete this integral. So I'll go ahead and then write the integral. So it is ql by 2 epsilon naught. So the integral will be minus 2 by square root of L square plus r square. So substitute 0 and r. Okay, so what is the flux finally? Okay, so if you substitute r, I think I'll get minus 1 by square root of L square plus r square minus small r is 0, so I'll end up having L. So we will see something like this, that 2 in the numerator can be ignored. So I have ql by epsilon naught minus 1 by square root of L square plus capital R square plus 1 by L. So if I send L inside, I can write the flux as q by epsilon naught into 1 minus L by square root of L square plus R square. Okay, so here, okay, so we are done with the problem, but let's say I want to take few more minutes on this. I want to point out something here. Okay, so here the flux is due to both the charges. and one charge is positive, the other is negative, both of them are generating electric field at all points on that circle to the right. Okay, so each charge is obviously providing the same amount of flux. So if I consider only positive charge, okay, so due to one of the charges, the flux will be half of this. So we can write this as Q by 2 epsilon naught into 1 minus L by square root of L square plus R square. Okay, so this is one thing. Now let us look at the geometry of the situation. So if I take any point on the ring and then join that point to either of the charges. So if I take this angle as theta, let's say take another point at the bottom of the ring and then join. So this is theta. So you see that the ring is kind of the base of a cone here. The ring is the base of a cone. So through that cone, when the semi vertical angle or the half angle at the vertex of the cone is theta, we can say that the flux is Q by 2 epsilon naught into 1 minus cos theta. Okay. Now, so now if you have this positive charge at the center of a sphere, so let's say if I take a sphere, so through a complete sphere, okay, so what is the spelling? So through a complete sphere, what is the flux? The flux is Q by epsilon naught. Okay, so but here we have Q by epsilon naught into 1 minus cos theta. Now, if you know a little bit about solid angles, the solid angle, when you are looking into all sorts of directions, so when you have a sphere, if you are looking into all directions, you are really looking at a sphere. Okay, so the solid angle for a sphere is 4 pi steradians. So let me write it here. Solid angle. Okay, so you can say if you are looking at a complete sphere, is 4 pi steradians. Now in this case, you would get a flux of Q by epsilon naught. Okay, but here if I substitute 4 pi, let's say, I mean, if I'm trying to say that if I have, let's stick to this. So instead of taking the entire sphere, if I just take a portion of the sphere, okay, now the electric field lines are just coming out of this circular region, okay, where the semi-vertical angle of this cone is theta. So in that case, the solid angle, if the plane angle is theta, okay, plane angle, so we are taking half angle of the cone. Okay, so if the plane angle is theta, then from here I can say that if I substitute 4 pi instead of Q by epsilon naught, okay, I can say that the solid angle will be 2 pi into 1 minus cos theta steradians. So which you can use to solve some flux related problems going forward. Okay, so but you have to understand that this theta is not the angle at the vertex, it is half of the angle at that vertex. So if you take that semi-vertical angle, you can, I think you can call that. Okay, so if that angle is theta, then the view that you get out of this cone, okay, in terms of solid angle, is 2 pi into 1 minus cos theta steradians. Okay, so out of 4 pi steradians, the flux is Q by epsilon naught. So out of, let's say, 2 pi into 1 minus cos theta steradians, this is the flux that you will get.